Now that we've laid out our procedure for analyzing different physical systems, it seems as good a time as any to take a look at a specific physical setting. For our example, we take electromagnetic interactions involving electrons and their antiparticle partner, the positron. This example will go a long way towards uncovering many of the hidden features which underlie the structure of the Standard Model, and, for that matter, particle physics in general. In the first place, we see that to discuss interactions involving a fundamental particle, like the electron, we must introduce the concept of an antiparticle. In fact, every particle in the Standard Model has associated with it an antiparticle partner. Think of the antiparticle as being like the evil twin sibling of their Standard Model brother. Though they share the same mass, all their other quantum numbers, including charge, color, and flavor, are completely reversed. The first step in analyzing any problem in particle physics is to write down the Lagrangian, which is to say, to program our GPS. To program the Lagrangian, we need only specify all the particles and interactions we are interested in seeing. Associated with each particle and interaction is a term in the Lagrangian, with the total Lagrangian being the sum over all such terms. We're interested in electromagnetic interactions involving electrons and positrons. If we recall that the electromagnetic interaction is facilitated by the photon, we conclude that our Lagrangian must include three terms. One term associated with the electrons and the positrons, one term associated with the photons, and one term associated with the electromagnetic interaction itself. Technically speaking, the term in the Lagrangian associated with a given particle introduces a quantum field associated with that particle. Without going into too much detail, the quantum field of a particle gives us an idea of the number of that particle present at each point in space and time. As such, each quantum field comes equipped with the ability to create and destroy its designated particle at any place and at any moment. The most important thing to appreciate about the quantum field is that there is only one for each type of particle, not one for each individual particle. What's more, you will notice that an antiparticle does not get its own quantum field. All of the information about the antiparticle is contained in the particle quantum field. Once the Lagrangian has been written down, we must designate the initial and final states of the transition we're interested in seeing. In translation, the starting point and final destination of our trip down particle physics lane. We may be tempted to take as our initial and final states any combination of the particles present in the Lagrangian. Ostensibly, this is entirely the case. However, if we pick our states entirely at random, we will come to discover that certain transitions, quote-unquote, occur with probability 0. This brings us to the tremendously important concept of conservation. Perhaps most familiar in the context of conservation of energy, the conservation of fundamental quantities in nature underlies all the physical processes we observe and provides structure for the form and function of every theory yet written in the history of physics. Deftly stated, the concept of conservation provides the rules for the game which is particle physics. It tells us what events are allowed and what events occur with probability 0. To understand laws of conservation, recall again our analogy between navigating the route from one place to another using a GPS and navigating the route from one state to another using the Lagrangian. We noted that the motion of a physical system could be encapsulated in the available streets or paths between point A and point B. If one chose to drive from point A to point B, they would similarly be limited in the possible options for how to do so by the geography between those points. For instance, we can't just drive over a mountain. In our case, the streets of our theory are determined by fundamental laws of conservation. Conservation of momentum, conservation of energy, conservation of angular momentum, and conservation of charge. These fundamental laws of conservation define the geography of our system, and therefore the kinds of streets that we can build between one state and another. Returning to our example, in constructing initial and final states for our electromagnetic interaction, we must satisfy the following requirements. The momentum and energy of each state must be equal, the charge in each state must be equal, and the number of electrons in each state must be equal. Visually, the streets of our theory are illustrated through the arrows and labels present in the Feynman diagram. Each straight line, corresponding to the dynamic evolution of an electron or positron, is labeled with a P or Q, which denotes its momentum. The total momentum of all particles at the bottom of the diagram, corresponding to the beginning of time, must be equal to the total momentum of all particles at the top, corresponding to the end of time. Upon each straight line, we draw an arrowhead, which either points in the positive time direction to denote a particle, or the negative time direction to denote an antiparticle. This underscores the fact that we could think of antiparticles as being negative particles, since they make negative contributions to the total charge and the total particle number. The charge and number of particles at the beginning and end of any event must be conserved. Thus, in our case, the total number of electrons minus the total number of positrons must be constant. A simple way to achieve this is to ensure that the direction of arrowheads going into and exiting any interaction node are concurrent with each other. In this light, it's sometimes nice to think of Feynman diagrams as depicting water flowing through a pipe. Like the amount of water, the conserved quantities described above do not change, even while they move throughout space and time. The laws of conservation limit the number of possible processes given any set of particles and interactions. From electrons, positrons, photons, and the electromagnetic interaction, we can form the following interesting processes: electron scattering, electron-positron annihilation, electron-positron scattering, and Compton scattering. Notice, we did not need to write a different Lagrangian for each of these processes. The Lagrangian containing electrons, photons, and the electromagnetic interaction contains within it all possible processes consisting of electrons, photons, and the electromagnetic interaction. With the Feynman diagram drawn, it remains only to evoke the Feynman rules in order to compute the path integrals of each event and thereby determine the associated probabilities of each transition.